Hi, welcome back. This video is a couple of examples of evaluating limits and giving you some techniques to evaluate those limits. And the theme of these two examples is, hey, rewrite the quotient. Rewrite the quotient without changing the value of the limit. Example 1. Let's evaluate this limit if the limit actually exists. If the limit doesn't exist, we'll support our answer. We're going to take the limit as x approaches -5 of the quotient of these two polynomials. Now, since we have a polynomial top and bottom, we can actually substitute -5 in for x directly as long as the denominator is not 0. So we try direct substitution. And I'll let you double check my calculations. In the numerator, we'll get -5 squared plus 2 times -5 minus 15. That sum equals 0. Now that's not a problem. It's okay if the numerator goes to 0. Here is the problem though, in the denominator. When we take x squared plus 6 times x plus 5, and we let x be -5, we end up with 25 minus 30 plus 5, and that's 0. Problem. We don't know if the limit exists or not because the denominator is 0. There's hope. We're going to find out if we get 0 over 0 upon substitution that there is hope. There is hope. Yay. There's hope that the limit will exist. Okay. So we actually start over again. We're going to rewrite this limit by factoring the numerator and the denominator, seeing if there's any common factors. Okay. I have a trinomial up top. The coefficient, the leading coefficient is an understood 1. So we're going to try factoring the trinomial into 2 factors, each starting with an x. Then we're going to look at the constant, which is -15, and ask ourselves, are there factors of -15 that add up to 2? Well, it looks like it's going to be some combination of 3 and 5, and the 3 is going to be negative so that the sum is positive. All right. The denominator should also factor. There's a leading coefficient of 1, so I'm going to record x times x. I'm going to look at the constant at the end, and I want the factors of 5 that add up to 6, if there are any. Well, that's going to be +5 and +1. Aha! There's a common factor of x plus 5. We know we can rewrite a rational expression by canceling common factors as long as we don't change the denominator. Since x plus 5 would be 0, if x were -5, we need to restrict the domain of the function. But we know from evaluating limits that the value of a limit does not depend on this number here. So we can rewrite the limit equivalently as x minus 3 over x plus 1. And the value of that limit will not depend on x equals -5. Okay. Suffice it to say, you can cancel factors if you're under the limit. So the limit has not changed value. And now I can use direct substitution. Everywhere there's an x, I'll replace it with a -5. I will simplify the top, simplify the bottom, and it looks like the limit does exist and has a value of 1/2. Okay. And remember what that means? As x gets closer to -5, the output of the original function gets closer and closer to 1/2. Okay. If you need to pause the video right now and take a look at those calculations, you sure can. We're just going to have one more example here in the next 5 minutes. So our second example looks a little different, but we're going to find a similarity in the way we proceed. Again, we're going to evaluate the limit if the limit exists. If it doesn't exist, we'll support our answer. Okay. Now, already we see, if we try direct substitution, the denominator is going to be 0. And that we can't have that. So we can't use direct substitution from step 1. Now, will there be any hope? Okay. If we did use direct substitution, the denominator would be 0. If we use direct substitution in the top, we would get 2 times 4 plus 1, or the square root of 9, and 3 minus 3 is 0. The numerator would go to 0. Yes, there's hope. Because 0 over 0 is just a form of the problem that does give us hope that the limit will exist. Okay. But the hope comes in the rewrite. We take our original function, our original limit, and we're going to multiply by something convenient. We don't want to change the limit, so we have to multiply by something over itself. We're going to choose to multiply by the conjugate of the numerator over itself. Remember how we create the conjugate? We take the first term, keep it, the constant, keep it, just change the operation in the middle. So it's important that if there were a negative in the numerator or a minus, that becomes plus. Okay. So we're still evaluating the limit. We don't drop the limit symbols until we use direct substitution. We could use FOIL in the denominator, but I'm going to leave the denominator factored. And you'll see why I did that in just a minute. And you would make the decision after you have some experiences as well. Okay. And the top, to do this multiplication, I'm going to use FOIL so that I distribute correctly. I'm going to take the product of the first 2 terms. The radicals go away and I'm left with 2x plus 1. I'm going to take the product of the outside terms. That'll be positive 3 times square root. Then I'm going to take the product of the inside 2 terms. That'll be negative 3 times the square root. And last of all, I'll take the product of the last terms, which will give me negative 9. I want to simplify the numerator and see if I might have any common factors, top and bottom. Again, from experience, I'm going to leave my denominator alone with these 2 big factors. I'm going to concentrate on the numerator. Since I use my technique of multiplying by a conjugate over itself, this positive product here and this negative product here, they're going to add up to 0. So I might strike them out. They add up to 0. The other 3 terms, 2x plus 1 minus 9, simplifies to 2x minus 8. Alright, now that's looking better. You might recognize in the top we have a common factor. What is that common factor? 2. When we factor out a 2, we're left with x minus 4 in the parentheses. That's helpful. Okay. We remember from the first example, it's okay to cross out x minus 4 divided by itself. We know that we would be changing the domain of the function at one point. But under the limit, as x approaches 4, this limit does not depend on the value at x equals 4. So the limit in purple is equivalent to the limit in red, where I've simplified. Because the limit doesn't depend on the value at x equals 4, this limit in purple is exactly the same as the limit in red. The limit in red can be evaluated with direct substitution. We plug in 4 wherever there's an x. And we see that that value simplifies to 2 over 3 plus 3, 2 over 6, or 1/3. Alright, So there were two examples of evaluating limits by rewriting the quotient under consideration. All right. Good luck with your practice.